So without further ado, let me yield the floor to Keith and make sure that I'm able to. Oh, there he is, Keith.
If you can share your slides.
Yep.
Okay.
All right, that coming through?
Yeah.
Yes.
Okay, nobody told me that I was supposed to answer all the questions that were left unanswered in the first talk today, so I won't promise to do that. Yeah, one of the things that I do each time I agree to give a talk like this is I try to look for things that I haven't said before to provide some additional insight. And so it's one of the challenges of doing these talks is that I always want to give the audience some new insight and not just repeat the things that we've said before. So having said that, I looked at the rest of the talk lineups and realized that I had to include a marketing slide. So here's our Slingshot marketing slide. You know, one of the things about Slingshot is that we bring together Ethernet and all the good qualities of Ethernet, the ubiquity of Ethernet, the fact that your data center is pretty much all Ethernet, and the interoperability that that gives you and the native software support that gives you. So we'll run a TCP IP stack, we'll run a verb stack over Rocky and interface with devices in the data center. And we unify that with all of the things that we've always done with traditional HPC interconnects, which is provide low latency and efficient transfers for small messages as well as large messages, provide MPI accelerations. And then new in Slingshot, we bring congestion control in the fabric itself. We have enhanced our adaptive routing even relative to prior generations, and we're now running at scales that we have never run at. So we couldn't give a talk without providing some of the pictures of the Exascale systems out there, this Frontier on the left and the upcoming Aurora system on the right. And this is just some of the fun numbers from those systems that provide you a little bit of insight in what it means to run an Exascale system on Ethernet. So you'll see, you know, it calls out kind of the number of compute nodes, what a compute node looks like, and the bandwidths. And as we move to Aurora, we're talking about systems that have 1.6 terabits per second per direction into each node. That is a staggering figure relative to just a few years ago. The network has 166 compute groups with 32 switches each. So it's a Dragonfly network that gives you, when you include IO, that takes you up to 5,600 switches, 87,000 NICs, and tens of thousands of cables. These days, the cables are come in cable assemblies. So the L0 links are 2 links each. You've got L1 links that are 4 links each. And then when we get out to the optical reach, there are 2 links each again in the optical bundles. Total of over 240,000 200 gigabit fabric ports when you add up all of the switch ports that's in the device. Now to build a scalable system, so what I decided I want to talk about in this talk was a little bit about what it takes to build an exascale system and looking at that from the NIC perspective. The first thing you have to do if you're going to build a scalable system is to use scalable software. So what does it mean to have scalable software? Well, it means a lot of things to have scalable software, but when you start talking about the network stack, really the first piece of that is that you not have user visible connections. You shouldn't have users worrying about connections or managing connection state. And most importantly, you should not have state that scales based on the size of the application. It's okay if your state scales with the number of receives that you've posted, the number of messages you expect, the number of messages you have outstanding, the bandwidth, and the message rate. Those are okay, but when you start talking about scaling state with the size of the job, that's not, because you start looking at jobs that have 10,000 compute nodes, 60,000 GPUs, 80,000 NICs. You don't want to have state that scales based on those numbers. So the network API we export, just like the Cornelius talk earlier, is libfabric. LibFabric is has a connectionless design to enable one-sided operations and two-sided send receive operations, including matching, atomic operations, triggered operations. All of these are features that kind of were inherited from Portals 4. The overall design was influenced by PSM. All of this was put together as part of the Intel OmniPath program. Now LibFabric is shipping from many vendors. We ship LibFabric. That's the API available on the AWS EFA NIC. It's from Cornelis, and there are others that are shipping it as well. Okay, so just a quick look at the NICs. So yes, I guess we call them Slingshot NICs now. I still think of them as Cassini. On the left here is Cassini 1. That is the NIC that's in Frontier, that's in Aurora. That's 2 NICs on a single die. They are completely separate. Each one has a 200 gig link, and each one has a PCI Express Gen 4x16 host interface. It's on a TSMC 16 nanometer process. More details there about the device. The middle picture here is Cassini 2. It's an upcoming device. It's a 400 gigabit per second NIC. Again, it's 2 NICs on a die. It has 2 400 gig links, 4x100s, that is, 2 PCI Express Gen 5x16 host interfaces, and that's on a TSMC 7 nanometer process. These parts are back. They're in the lab. They're looking good. Here's a bandwidth measurement, very preliminary, because as noted, every time you get back a new device and a new node, you have to retune the 2 pieces together. So you might ask, why do you keep putting 2 NICs on a die? They're 2 of exactly the same thing. There's no shared logic between them. Well, the reason we do that is if you look at the node architectures that people are been building lately, from the bottom left here, that's a Perlmutter node. And you'll see it has 4 NICs, which means 2 ASICs, hooked into a node with a CPU and 4 GPUs. The top middle one is the Frontier node. One of its interesting characteristics is that you'll see the NICs are directly connected to the GPUs in that picture. So there are 4 GPUs, and each GPU has a direct connection to a NIC. And on the right is the Aurora node. Now I need to get a copy of that picture that was used in the first talk this morning, because it's a little bit better picture than I was able to snap for that node. But it's got 6 GPUs and 8 NICs. And so, when you are packaging 4 or 8 NICs with every node, then there's a packaging efficiency by putting 2 NICs in a device. Turns out very few people ever ask us about having 3 NICs or 5 NICs attached to these bulky GPU nodes. And so we do a 2 NIC per die packaging optimization. So one of the things I thought I'd talk a little bit about is our network transport. So our network transport has 3 paths through it. One of them is the ordered messaging case. So MPI headers kind of expect to be processed in order. And so we have an ordered messaging protocol. The state for that scales with the number of kind of active message. That's the wrong way to put those words together, because active messages imply something totally different in this community. But it scales with the number of messages that are currently in flight. The way we do that is we only maintain ordering state with a peer that you are currently communicating with. We pipeline the establishment of that ordering state. There's a very minimal amount of state needed to do that. And it's lightweight enough that you can stand those up and tear them down often. So if you wanted to send a message to each of those 87,000 NICs and sent, a kilobyte to every NIC in the system sequentially through it, you would stand up and tear down connections, and the user would never notice that as an overhead. It's lightweight enough to do that. The middle column talks about our unordered messaging path. So this is useful for in PGAS environments. It's useful for transporting bulk data after you've done the header matching. And this further enhances the scalability of the protocol because it eliminates the need for the ordering state. Really, MPI is one of the use cases that needs that ordering state, but a lot of other things don't. It doesn't really matter what order the packets within megabyte message are delivered. It just matters that they are delivered and that you know when they have been delivered. Most PGAS use cases don't require ordering. There's a point in the application where they do fencing to establish ordering between transactions, but other than that, they don't care so much. And so we have a protocol that doesn't require the ordering state, and that protocol truly scales with the number of messages in flight. There's no additional tracking beyond tracking the outstanding messages that are in flight. And then there is a third protocol. So a lot of PGAS implementations use a response so that you know when the packet has been delivered. And one of the challenges there is that a response has kind of got to be at least of some minimal size. These days, you know, kind of an Ethernet frame, we do some optimizations around the edge of the frame, so we actually get down to a minimum frame size that's smaller than what you'll find on traditional Ethernet networks. But you're still talking about, you know, something like a 48-byte frame or something that's kind of a minimum size that every response is going to take. And you need that to know that the message has completed. You need it to implement reliability. You need it to implement defense semantics. Except really all that you need to know in most PGAS applications is that you have finished all of them. And so when you have a reliable network that doesn't drop packets, those responses for every message are overkill. And so we have a path through the network that allows the switches to aggregate together that completion information, which dramatically reduces the overhead associated with the smallest PGAS transactions. So if you want to do 8-byte transactions and do them all over the system, we have a path through the system that will allow you to aggregate those responses so that it mitigates that overhead. So another thing that we put a good bit of energy into is offloading tag matching and offloading rendezvous operations. So, you know, many real applications have big messages. Big messages tend to use rendezvous for their data transfer. They tend to be bandwidth sensitive, and overlapping computation and communication can allow you to hide a lot of that data transfer time. And so we offload rendezvous, and kind of the pictures to the right here illustrate why we do that. So if you don't have hardware matching and you post to receive and the message header comes in, you kind of wait while you're doing the computation until somebody calls the MPI wait, then it does the matching, then it pulls the data. If you offload the matching but don't offload the rendezvous, then even in the expected message case, you wind up with this idle time in the network, or there's a risk of winding up with this idle time in the network for rendezvous, where the message comes in, you do the match, and there's nobody to pull the data. You have to wait for the host to get involved again to pull the data. So we offload the rendezvous as well. So the message comes in, we do the match, the NIC issues the pull for the data directly, and that reduces the total runtime of the application. We also offload unexpected messages, and kind of the pictures to the right here highlight why. so the funny thing is, if you have unexpected messages and you're not offloading anything, that actually works okay. The message comes in, you post to receive, the software sees that the message had already come in, and it does the matching and issues the RD may get. If you have the hardware matching, but you don't offload the unexpected case, you just offload the expected case, then you are in the same scenario we were in the prior slide, where the message comes in, you do the match, and then you wait for the host to get involved to pull the data. But on the right-hand side here, the message comes in, the receive gets posted, and your NIC does the unexpected message offload, then the NIC can do the match and pull the data. And when your computation is done, your data is there. Now, one of the things we learned, and I didn't talk about this as a choice, because one of the things we learned a long time ago was that offloading matching without offloading unexpected messages is not a good idea. So this was something that Portals 3 did back in the late 1990s, and it was okay, because with the system architectures of the day and network message rates of the day, it worked just fine. But then with the Cray XT3, you know, it used Portals 3.3, and it's kind of split the expected messages on the NIC and unexpected messaging on the host. And what we learned was that it was a major impediment to message rate performance to have that split, because there's a round trip that's involved from the host software to the hardware with every receive that you post, which kind of limited the throughput. So you never even consider anymore offloading matching without offloading unexpected messages. It's just a question of, can you also handle that unexpected rendezvous case? All right, these 20-minute spots are short. So to wrap up, Ethernet always wins. Its most recent win is Exascale. You know, it's been a hard thing for HPC to accept for a long time, but here we are, and Ethernet is the network of choice in Exascale systems, because all the physical layers have finally converged to a single solution. If you're going to build Exascale systems, you have to focus on scaling throughout the design. That starts with a scalable software stack, then into a scalable transport protocol, and scalable NIC designs. Offload's really important. It's a key piece of enabling scaling out to the Exascale levels, is to have that overlap. There's a growing industry now of NICs that provide strong progression and overlap in ways that they didn't. Just 10 years ago, people were having serious debates about onload versus offload, and whether or not you should do matching, and whether or not that strong progression mattered. And today, everything is trending in the direction of, you know, that offload, that overlap is a critical feature. And the last observation here is that new trends are emerging in the node design as we go to Exascale. Locality is becoming increasingly important. When you start talking about nodes that have 800 gigabits per second or 1.6 terabits per second per direction of bandwidth, it's getting more and more important that the NICs be close to the memory that they're accessing, because moving that much data across the system bus is getting really interesting. And just one more generation out, you start scratching your head and saying, I wonder how the system buses are going to pull that off. All right, I think that left time for a question, maybe.
Let's first thank the speaker. Questions, guys? I'm standing between you and coffee, so I won't blame you if you want to go and get it, but Keith is available here. So I think, yes, Ryan.
I'll ask a quick question. Keith, I officially disown multi-receive in OFI.
Okay, so Keith, Ryan officially disowns multi-receive, okay?
You said Portals 4 and Foundation, so I just want to make clear that that was not part of Portals 4, but is part of OFI. The other question that I had for you, Keith, was just, we've been talking a lot about disaggregated memory systems and CXL here and that sort of stuff. you said right at the end of your talk, memory bus issues are becoming really interesting. Do you foresee any interesting interactions between CXL disaggregated memories and bus speeds for next generation NICs?
There's all sorts of interesting interactions that are going to happen there. One interaction that's going to be a little bit interesting is that you're going to have to figure out where to plumb all of those things into the node. So if you if you look at some of the node pictures, if you have 4 NICs or 8 NICs that are plugged into your PCI or CXL, I mean, people kind of use the same pins for both. Like, where are you going to plug in the memory? How many of those ports exist on the system? So that's going to be an interesting question. Next interesting question is going to be, how many of those ports can run at full speed concurrently? Because if you look at the amount of bandwidth load that is being put on the edge of the die, it's a lot. And, really you should see what is the performance modeling that's been done on the interconnect, on the on-die interconnect for the processors and whatnot, when you start saying, okay, I've got, 8 200 gig NICs over here, and I've got 8 channels of CXL over there, and what happens when I transfer data from one to the other? And it's not an easy problem. And if somebody tells you it is an easy problem, look at them a little askance, because it's not an easy problem. I'm not saying nobody will solve it. I'm not saying it's not been solved for the systems that exist for the bandwidth they have at the edge of the die. But, kind of as we move forward and those bandwidths creep up, and you start talking about PCIe Gen 5 and PCIe Gen 6, it's a lot of bandwidth at the edge of the die.
Thank you. Thanks, Kate. So let's take a short coffee break. We'll come back in 4:30.
Thank you for being a wonderful and patient audience and for all the wonderful questions. See you in like 15 minutes, guys.